In this tutorial, we'll discuss the basics of character LCDs. The character LCDs are natural transition from 7-segment displays. For a tiny microcontroller, displaying characters comes in very handy in a whole lot of projects where you want to display information. This is one of the widely used visual displays for microcontrollers. Now, by character displays, we mean we can display characters, all the ASCII characters, and even some custom special symbols. Then these come in various color in the sense not of the text but of the background or the backlight. So the most commonly used colors are green and blue. The LCDs of character LCDs are of different types. By types we mean the size. So we have LCDs which display 16 characters in a single line. Then we have displays which show 16 characters in 2 lines, so total of 32 characters. And also we have displays which display 20 characters on 4 lines. And we also have 128 cross 64 displays which have 128 cross 64 pixels, and you could even display pictures. But this tutorial will confine to just the character LCDs, wherein there's an inbuilt controller called the graphics controller inside the LCDs, which takes commands from an external microcontroller or any other device and then displays characters. LCDs. This session will be divided into 2 parts. In the first part, we'll discuss all the basics that are required to get the character LCDs working, and in the advanced part we'll be discussing the internal details of the graphics controller for the LCD and a whole lot of details. So if you just want to get your character LCDs working, the first part would be enough. So in the basics, we'll discuss the pin diagram of LCDs, the 4-bit mode, the 8-bit mode, and we'll discuss in brief about the display controller. Then we'll see what are the basic commands for it, and after that we'll see the boot sequence or initializing of the display, and then we'll send some commands that are required to clear the LCD, then set the LCD at home position, number of lines, and the matrix, etc, etc. And we'll also send data, as in we'll send some strings, and we'll see. So in the advanced session, we'll see the HD 4870 in much detail. We'll discuss its internal block diagram, then its structure of its DD-RAM, character graphics ROM and RAM, and we'll discuss all this in great length. We'll see what is the relation between DD-RAM and the CG-ROM, DD-RAM and CG-RAM, and we'll see how to display custom characters on LCD, and we'll also discuss in length about the BZ flag and the boot sequence with BZ flag for 4-bit and 8-bit mode. Alright, let us move ahead and look at the pin diagram for our character LCD. In this entire tutorial, we will be discussing a 16 cross 2 LCD. So as said earlier, it displays 16 characters and 2 lines, but you can extend the concepts as well to interface a character LCD of say 1 cross 16 or 20 cross 4. So let's just go ahead and look at the pin diagram, and this would be similar to other character LCDs as well. So let's start with the power. So most of these LCDs work either on 5 volts or 3.3 volts. So let's say this is 5 volts. Now also, as we know that each of these LEDs has a backlight, and this backlight needs to be turned on, and to do that we have 2 pins, and it is as good LED inside. So we can connect the anode to VCC and cathode to to ground. So, and also some of the, you should look into the data sheet and find out if this needs a current limiting resistor as with the LEDs. Now there is also one more pin related to power. It's the VD, or the contrast pin. So what this does is this controls the contrast, and usually what is done is a potentiometer is connected between to this pin. So if we vary the part, the contrast varies, the LCD contrast varies. And we'll discuss about this in a little more detail. And I've connected it to the wrong pin. Let me just correct that. Okay, so this is the contrast. Now, apart from these basic pins for power and contrast, we have 8 pins DB0 to DB7, which form the data bus of the LCD. Now we could use the entire 8 pins while communicating, and if we do that, then the LCD will be in 8-bit mode. So it will receive data in 8 bits or a byte. So we can as well decide not to use the first 4, so DB0 to DB3. And a point to remember here is, whenever we're using just 4 bits or in 4-bit mode, only the higher 4 bits DB4 to DB7 are active. So we cannot use 4-bit mode from DB0 to DB3. So whenever you're using 4-bit mode, it should be pins DB4 to DB7. So this can be also operated in a 4-bit mode. Now, the only remaining pins are the resistor select, read write, and enable. Now the resistor select pin, if this pin is 0, the command register inside the LCD is selected. If this is 1, data register is selected. Now what is the difference? Now the basic commands from the LCD, for the LCD from the microcontroller, could be to clear off the entire display, or to take the cursor to the home position, or it could be to set the display type as to 4, or a display type as to a 2-line display or a 1-line display, or it could be setting the mode, 8-bit mode or 4-bit mode. So these are all commands that we send to the controller. Now if register select is 1, we send data to the LCD. So data to the LCD could be all the ASCII characters. I mean, not all, but most of the ASCII characters, the numbers 0 to 9, letters A to B, small ones and the big ones as well. So all these, and again with a few special symbols. So all this is data. So the LCD has a ROM, a permanent memory, which has character codes that correspond to each of this ASCII digits. Like if we send ASCII 0, that is 30. So if we send a hex 30, the character generator inside the LCD, so we'll discuss this. So it converts it to matrix or dots, and then it displays 0 on the LCD. So this is basically the data for the LCD. So the register select, when it is 0, we send a command. When it is 1, we send data. Now the next pin is the read write. So now, as for the name goes, the when the read write pin, so let me just write it. So this is the read write pin. If read write pin, we can call it as read/write bar. So when the read write pin is 1, we do a read operation. So with this we can read data from the LCD. So this is done in instances where we are reading a busy flag, or we want to check the contents of the internal RAM of the LCD. So we do, or RAM, or in fact any other command that we have sent. So this is the read operation. So write is always used. It is used to when this read/write bar is 0, we can do the write operation, and this can be with respect to writing a command or writing data. So moving further, we'll see the combinations and what actually is used with respect to read write. And the last pin here which remains is enable. Now enable is kind of latch pin. So whatever commands or data that we send to the LCD, it needs to be pulsed by enable. So when we send a high to low pulse, in fact the thing is something like this. So we should have the data ready on the data lines, and then we should also have selected the register select and the read write, and then if we send a pulse on the enable line, the data gets latched. So it's kind of a gate or the control for the entire LCD, and this is particularly useful for synchronizing the timing between the microcontroller and the LCD module. Now let us go ahead and look at the commands and the data, or rather the combinations of register select and read write. So now if this is the register select and if this is read/write bar, now if it is 0 0, when register select is 0, a command, as we have discussed, the command register is selected, and when read/write bar is 0, write command, the write operations is selected. So with this combination, what we get is command write. When the register select is 1 and read write if it is still 0. Now when we do register select as 1, the data register is selected. That means we are sending data from the microcontroller. So this would be command write. Now for the next operation, if we make the register select or the read write as 1, so this will basically the read operation, and when we do it 0, we call it as command read. Sorry, it would be data read. Since it is register select is 0, it would be data. Sorry. Alright, so the next command, the next combination would be making register select 1. If we do register select as 1, so the data register would be selected, and if we keep this as 0, then we would be writing data. So this would be data write. Now if we make read/write bar as 1, we would be reading from the LCD. So for the read, again there should be 2 cases. So one, if it is 0, then this should be command read, and if it is 1, it would be data read. Now again, to do a recap, the command read is frequently used to send various commands to set up the LCD. Data write is the actual data that we want to display on the LCD. Now if we look at command read, this is done in very few instances where we want to know if the LCD is busy. So for example, to check the busy flag. Now the last option is rarely used. We rarely read data back from LCD. Now let us go ahead and look at the controller that is present inside the liquid crystal display, or you could call it as a display controller. Now most of the LCDs use HD 44780 or a compatible controller inside them. So this is ASIC which has been is hardly one of the ASICs which remain same for years. So this ASIC has been used from past 25 years and hardly there are any changes in it, and there are lot many controllers out there with this or a compatible controller. Now what you could see is these are all the interface pins as we have discussed, and this is the data bus. What it does is it takes all the commands and data and it stores in its internal RAM, and we'll discuss in depth about this in the advanced session. And what it does is, so it takes all these data and commands, and then there is a character generator inside it which generates specific character patterns, and then it displays on the LCD panel. So this is the LCD panel. Now if you're wondering what the 16 common lines are, or the 40 segments are, or what the segment driver is, we'll look at all this in detail. But if you want to just interface LCD, you rather not need them now. So let us go ahead and look at some of the commands that are used for the LCD. Now so let me just write it down here. So say this is our register select and this is our read write, and then say this is our data bus D7, D6, D5, D4, D3, D2, D1 and D0. Now for this would be for where the LCD would be in 8-bit mode, and it would be similar for the 4-bit mode. The only thing is, instead of sending all the data, all the 8 bytes, because there will be only 4 bits connected in the 4-bit mode, so what we do is we split the commands into 2 4-bit nibbles and then send. We send the lower nibble first, and then we send the higher nibble in the 8 bits, but all the commands remain same. Now so and from the previous discussion, what you could see here is, so since all these are commands that we send to LCD, the register select would always be 0 while sending all the commands, and the read/write operations line will always be 0 since we are writing a command to the LCD. Now there is a peculiar fashion for this command, and they started with the LSB. So if this is the one, this one shifts through the instruction set towards left. So this particular one, when bit, if it is 1, then this is a command to clear the display. Now and also you need to remember that all these commands, all these commands where register select is 0 and read write is 1, or rather for all commands of LCD, all these needs to be pulsed by enable. So for all these commands, enable should go high and then it should go low. We'll discuss in detail the timing diagrams. So this is your LCD clear display. So if I go ahead and write the hex code here, it would be 0x01. Now the subsequent commands start, the one starts shifting to the next digit. Now this command with all zeros, and this is don't care basically. So this command, it gets the cursor home. Even in the LCD clear display command, the cursor comes back to the first position and the entire display is cleared. Basically RAM contents are cleared. So but the difference between these two is it just gets the cursor back to home. It does not clear any of the contents. So again for this register select and read write is 1. Now and the hex code would be 0x02 or anything 0x, even 3 would not make a difference. So it's 0x02. Now the next is again proceeding with the same thing. The one shifts here, and this bit, it's called I/D, wherein it stands for increment or decrement, and this S stands for shift. Now as we have two combinations for each of this, basically there would be 4 combinations of this. So when both are 0, when S is 1, when ID is 1, and when both are 1. Now this, when increment and decrement both are 0, so we can call this as D bar. So the cursor will decrement by itself, and if S is 0, the display will not shift. The character which is displayed will not be shifted. So what we mean here is, like, say a character is displayed here, A. Now if we decrement the cursor would point to the previous location in the RAM, and then the letter itself will not shift. Whereas if we keep the decrement option turned on, and if we make S1, even the letter A would shift back and the screen would become blank, assuming this is position 0, 0. Similarly, if instead of decrement, if this bit is 1, it would increment. After displaying this character, the cursor would go to the next position if the shift is 0. Now if the shift is 1, so it would also shift the character to the next position. So basically we mostly use increment the address pointer, and then we do not shift the display. So this is a widely used command. So this I could write it as 0x, this is 4, and this would be 0x06 if I take it as 1, 0. So that would basically mean increment, but there is no shift. Alright, so this is basically a command which decides increment and shift. So again for this as well, the register select and read write lines would be 0. Now let us look at the next command. So for the next, again the one shifts here, and all these are 0, even the register select and read write is 0, and this bit is called the D. It stands for display. When display is So okay, when display is 0, the entire display is off. When it is 1, the display turns on. And the next is cursor. So the cursor that you have in LCD, if it is 1, it is turned on. If it is 0, it is turned off. And the last bit is called the blink or the B. So if this is 1, the cursor blinks with the character. I mean, say if A is displayed and the current position of the cursor is on that particular position, so the character blinks itself. So by default, what we do is we turn on the display, the cursor is turned on, and the character is not blinking. So if we see that, then the combination would be 0x0e. Now, so this is this we could call it as display on off control. Right, for the next command, the 1 moves here and all the remaining bits are 0. So register select and read write remains 0. And so okay, so this, so as these two are don't care. So now the next bit, it's called the S/C, and this is R/L. So if this bit is 1, it shifts the display, and if this bit is 0, it moves the cursor, and this sets the direction for the shift or the cursor. So if it is 0, it shifts to left, okay, or the cursor will be moved towards left. So if it is 1, it moves towards right. So usually we do not shift the display, we just move the cursor. So this bit will be 0, and we usually move it towards left, so this bit will be 0 as well. So the hex code would be so the four bits are 1 and the next 4 bits are 0, so this would be 1 0. Now similarly, the next command and the next is an important one. So for the next command, the 1 shifts here. Alright, so the 1 shifts here, and the next bit, it's called the display length, or the data bus length, we could call it. And then the next bit is N. It defines number of lines the display has, if it is 1 line or a 2 line display. And then there is font size F. Now this is a rather important one. So, and again everything else remains 0, so we could assume the don't care bits as 0 as well. So now what you could see here is, if this bit, if it is 0, then the display length that is selected is 4 bits. So it means out of the 8 lines that are used to display, as we have discussed before, only D4 to D7 will be used for the interface. If it is 1, it would be in 8-bit mode. Now when N is 0, it would be a 1 line display. So it would be 16 cross, for a 16 cross 1, it would be this bit would be 0, and if it is 1, it would be a 2 line display. Now the font size is of 2 types. So if F is 0, it would be a normal 5 cross 8 font. So what we mean by it is there will be 5 columns and 8 rows that make up a character. So if we display A, it's not proper, so this is just a matrix of 5 cross 8 dots, and if it is 1, it would be 5 cross 10. So now we can make the combinations for 4-bit as well as 8-bit mode from this particular command. So let's say for the 8-bit first, so we have DL as 1, then we have number of lines as 2, because we are discussing in context of 16 cross 2 LCD. So this would be 1, this number of lines would be 1, and we would go with the default font size. So in this case it would be 0x, then this is 2, and this is 8, so this would be 0x to 8. Okay, so in fact this would be this would be 1, so this would be 3, 8, and for the 4-bit mode it would be 0x to 8. So this is for 8-bit and 2 line, and this is for 4-bit 2 line. Alright, so the next command, for the next command again, the 1 would shift here, and for the next command again, the 1 would shift to the next position or the last position. Now this ends all the commands where read write are both zeros. That means we'll be sending commands with this particular combination. So this will be 0, 0 and 0, 1. Now these are again two important ones, but the important point to note here is this particular command, it sets address for CG RAM. So this is used only when we are displaying custom characters, which are not doing in this beginner or basic video. So for the next video you could see the combinations with this command. So this is basically used to display custom characters on LCD. And the next command is, it sets the address for DDRAM, and this we would be using. Now what this does is, this bit is 1 and we have 7 bits left, so the address range would be 0 to all ones, which is 127 in hex. But again, we do not use all of this, we just use 80 addresses, and since this bit is 1, the first address would be 1 with all zeros, which in hex is 80, and for a 16 character display, this 80 would go from 80 to 8F, and the next bit would turn on here. So for the next range, so this would be 1100, so this is for the second line, it would be from C0 to CF. Now this is all about setting the commands, sending the commands. And if we send a command to display a character, and this defines the position on the LCD. So these are 16 characters on first line, and these are 16 characters on second line. So if we send this particular command as say 80, the display will be on the first position of the LCD, and next what we need to do is, we need to send the data that is to be displayed on this. And to do that, the register select becomes 1, and we are still writing to the LCD, so this becomes 1 and 0, and whatever we send here, the next 8 bits, so the next 8 bits, whatever we send, these will be displayed on the LCD. Now say for instance we send the ASCII value of 0, so that is 0 0 0 1 1, so this is 0x, sorry, so this would be, sorry, the ASCII value for 0 would be 30, so it would be 0 0 1 1 and all zeros. So if we send this, 0 will be displayed on the LCD. So this is send data command. Now we will discuss about creating custom characters in the advanced video, and a whole lot of other details as to since we have 127 addresses but we're using only 80 of this, or eventually we're using only 16 for the first line and 16 for the next line, and we will discuss the internal RAM structure and its relation with the CG RAM and how it generates the characters from the given ASCII value. So we will discuss all that in the detailed video. Now moving ahead, just go ahead and look at the timing diagrams for the 8-bit mode. Now this would be similar for even the 4-bit mode. Now one thing that you need to remember all the timing diagrams is the enable pulse. So that plays a very important role. Now as we have here, so the register select, so say this is our register select. Now this could be 1 or 0. And then we have our read write, this could be 1 or 0. We have the enable pulse, this could be 1 or 0, and we have the data bus, so this could be 4-bit or 8-bit. Now there are a few important timings that you need to take care of. Now say this is, let us start with the register select, and the next is, say this is read write, and this is enable. Now before we send command or data to the LCD, we should ensure that, the enable is the gate for sending commands or data to the LCD. So even before we do that, even before we give the enable pulse, the register select, read write and the data lines should be set up. Okay, so like say for instance we are writing a command. So this is what we usually do while setting up LCD. So when we want to write a command, the register select would be 0. So if it is 1, then we have to make it 0. And so this is 0. We are doing a write operation, so again the read/write bar would be 0. So and we have placed the data on the data bus. Now this could be here, we could start not in the beginning, but once we set up the lines we send the data. So let's say we start here. So this is the data. Alright, so now the important thing is, before we send an enable pulse, this should be set up, and this is called the address setup time. Like we need to say send a low to high pulse, And so this time is important, and we should, before giving a command, the register select, read light, and the data lines, they should be set up for a minimum period, and this is called the address setup time. And this should be 40 nanoseconds. This is a minimum of 40 nanoseconds. And once we do that, and we send a high to low pulse, and after we have these commands, it should hold on to that particular state. After we pulse the command, it should not go up immediately, rather, so it should hold on to the state for a particular time. Like, say our enable pulse ends here, and there is in fact a duration for the pulse as well. So let's say the pulse ends here, so this should stay low for a certain time, all the lines, and this time it's called the address hold time. So this is PAS, this is setup time, and this is TAH, this is hold time, and the hold time is 10 nanoseconds. And the duration of the pulse width, so this is not up to scale, so this should be minimum of 230 nanoseconds. Now, if you are interfacing a slower microcontroller, like say 8051 or AVR or PIC that runs up to 20 megahertz, you need not rather worry, and you can give delays in microseconds, so that would suffice.